In this video, we're going to take a look at a much more precise method for doing vector addition and subtraction. And this is considered the component method or analytical vector analysis. But basically, it's going to mean that we're working with numbers and using our calculators. However, at the heart of the methodology is a head-to-tail diagram. And you want to use a head-to-tail diagram so that you're properly visualizing your vectors, and those vectors which point in a negative, or I should say those vector components which point in the negative direction, get properly labeled as a negative vector. The process that we're going to go through is to first draw an HTT for visualization purposes. Then you want to determine your vector components of each individual vector and put them into the table that I'm about to show you. Then you're going to add up all the x components separate from all the y components, and that's going to give you a resultant in the x dimension and a resultant in the y dimension. And these two resultant vector components represent the components of the resultant vector. So every vector that's not horizontal or vertical is going to have components. And then you determine the magnitude of the resultant by using the Pythagorean theorem because you're forming a right triangle. And to get the angle, you have to use trigonometry. So just like we used sine and cosine to determine components, we'll now reverse the process and we'll determine the angle based on the tangent function. So let's take a look at an example of vector addition using this strategy. The first vector is going to be 55 meters long, and there's an angle of 38 degrees. I'll draw that in a minute. Then we have another vector which is 10 meters pointing due east, and then our third vector is going to point down and to the right for 35 meters. So that's going to be a little bit shorter than the first vector I drew. In fact, to get our scale approximately right, I'm going to lengthen this one. Okay, so we have here, this is 55 meters, and the angle that it makes is 38 degrees. This one has a length, this is D2, this one is D1. D2 is equal to 10 meters, and D3 is equal to 35 meters. And the angle that we get is measured from the vertical, and this is 55 degrees. Okay, so what we're going to do is just add up vector A, vector B, and vector C. So what we're doing is this: D total is equal to D1 plus D2 plus D3. Now, looking at this, you might be inclined to say, well, that's just 55 plus 10 plus 35. But we're dealing with vectors, and that's what that symbol above the letters mean. So you can't just add them up straight, because one of these vectors points to the right, but another vector has a component which partially cancels because it's pointing to the left. So this is where the HTT is invaluable. So let's find the components for these vectors first. So vector D1 has an x component which is equal to, now the x component points like this, and the y component points like this. For D3, the x or the y component points straight down, and the x component points straight right. And there are no components to vector D2. So D1x is equal to D1 times, now the x component is adjacent to our angle, so that becomes cosine of 38 degrees. And that value is going to be 43.3 meters. d1y is equal to d1 sine of 38 degrees. And so that becomes 55 sine 38, or 33.9 meters. D2, we don't have to worry about any components because it's all horizontal, so we'll acknowledge that later. And then finally for D3, D3x is equal to D3 times, now notice that the x component is opposite the angle. So this becomes D3 sine of 55 degrees. So D3x is equal to 35 sine 55. So that's 28.7 meters. And then D3y is equal to D3 cosine 55. And that calculates out to 35 cosine 55, 20.1 meters. Now, did anybody pick up on the mistake? Already, it would appear that we have a mistake. If you said that D3y was negative, you would be correct. That is our first mistake because the y component points down. We have a second mistake, and that's going to be D1x, which happens to be negative because it points to the left. So when we do head to tail, or when we do the component method of vector addition, this is what we're doing. I'm going to start with D1, and I'm going to do D1 plus D2 head to tail plus D3 head to tail. And that's going to give me a resultant that looks like this, based on at least my approximation with my HTT. So what I can see from this, if I've drawn everything properly to scale, is that it's going to be pointing pretty well straight up. I'm not exactly confident with that. I don't think I have my scales right, but let's see how it goes because, like I said, this is going to give us just an idea of what's going on. All right, but again, using our components, this is what we're doing. So we take all of our components and we add them up head to tail. And we just start with the same origin. We have one here. There's a component. Then here's a component. And then we have another component. And then another component. And then there's one more. And that's going to be D2. I didn't draw any components for D2, so I'm just going to move that vector. And you can see that D2 brings us back to this starting point. So with this point in space right here being the starting point, you can see that our resultant vector is pointing to the same location, regardless of whether we use components or the actual vectors themselves. So let's put all of this back because we need the space to put in our table. Okay, so what we're going to do now is lay out our table. And everything in this column is going to be X components. Everything in this column will be Y components. The first row represents D1. The second row represents D2. The third row represents D3. And the fourth row represents d total, which is the resultant vector. Now, when we went through this process, to get the x component, we used d1 cosine of theta. So it's d1 cosine theta 1, and we used d1 sine theta 1 for the y dimension. For vector 2, we have just d2 in the x dimension. There is no trig involved with this, so I'm just going to write that as d2, but the y component was 0. For d3, the x component is positive, and it's d3, the x component we used sine, so d3 sine theta 3, and the y component becomes d3 cosine theta 3. Now, one thing I haven't mentioned, and that is the angle theta, it's always going to be between 0 and 90 degrees. It's always going to be between those two. You're not going to be using angles which are greater than 90. Well, now what that means is that it's going to be impossible to get negative signs from your trigonometry. So that's why you have to pay special attention to which way it's pointing, and that's why the head-to-tail diagram is so important. So let's go ahead and fill in our negative signs on this. Make sure that we don't forget. So the x component of vector 1 was negative. The y component was positive. Vector d2x was positive. No y component. Vector d3x is positive, but d3y is negative. Okay, so now let's just substitute in our values so that they're there conveniently. And d1x is minus 43.3 meters. d1y is equal to 33.9 meters. d2x was equal to 10, and we already know that d2y is 0. d3x was equal to 28.7 meters, and d3y is equal to minus 20 meters, 20.1. Okay, so all you have to do now is literally just add these up. And this is what we get. A minus 43.3 plus 10, I'm adding going in the down direction, plus 28.7. And that's going to give us a minus 4.6. Now we go to the y dimension, and we have 33.9 plus 0 plus a negative 20.1. And that's going to give us 13.8. So you can see that this is actually a fairly vertical line because it's 13.8 units up, but only 4.6 units to the left. So the reason it appears that my resultant vector using a sketched head-to-tail diagram is vertical is because of inaccuracies due to my estimating the length of the vectors. But this demonstrates that the strategy is there to simply help you to make sure to give you confidence that what you did with your math is accurate. So I would say that these are in agreement. Hopefully it's going to be a little more accurate than this, but it is nonetheless in agreement. Okay, so now what we basically have are the x components and y components of our resultant vector. And our vector, if we draw it a little more accurately, it's going to look more like this. And what I'm going to do is I'm going to stretch this out so that it's easier to see our components. And now we're going to do the last part, which is a lot of math, but it's not hard. So the thing to remember is that this is now our resultant vector. We are 4.6 units to the left. So that's going to be 4.6 units in that direction. And it's going to be 13.8 units straight up. And you can see that even this is not drawn accurately. I'm exaggerating that angle a little bit so that it's easier for us to see what's going on. Okay, so what we're looking for is d total, which is the blue line. And to get the magnitude of d total, we're going to use the Pythagorean theorem, which is the square root of dx squared plus dy squared. And I'm referring to d total whenever I say dx and dy. So the magnitude of the displacement, or how far, is going to be the square root of 4.6 squared plus 13.8 squared. So d total is equal to the square root of 13.6 squared. No, check that. The square root of 4.6 squared plus 13.8 squared. And that's going to give us a length of 14.5 meters. The angle, you can use any one of your trig functions because now you know the hypotenuse. We know that this line has a length of 14.5 meters. We know that this one has a length of 4.6 and this one has a length of 13.8. So you could use whatever trig function you want to use. However, way more often than not, we use the tangent function. And the reason for that is I've got the y component and the x component. So we'll use the inverse tangent of, now this is going to be the y over the x. Okay, so this is dy over dx. Now, one of the things I need to talk to you about is determining direction for the angle. We need a reference point for the angle. So if I give a reference, or if I do the calculation as y over x, what I'm giving you is an angle measured from the horizontal axis because it's opposite. If I sketch this in real quick, all right, there's our axis. It's going to be, our angle is going to be here, and the opposite side is the y component, and the adjacent side is the x component. So y over x gives me a reference angle from the x-axis. If you do it as x over y, then you get a reference angle from the y-axis. Both angles are correct, but you need to pay attention to how you did it so that you're properly expressing the angle, because often you're going to be told to give the angle as measured from the x-axis. Sometimes we're tasked with determining the angle, or we're given an angle in terms of north, south, east, and west. And the way we do that is actually kind of neat. It's pretty simple. But the y dimension gives us north or south, and the x dimension gives us east or west. So when you're looking at this, you just read going down. Now, one thing you never do is you never put negative signs in here. So no negative signs in your trig. Okay, the negative sign will be taken care of whenever we say west or south. Now, the way we do this is, if this were, say, looking down from a helicopter view and we're looking at a map of the earth where we can use north, south, east, and west, what we do is we say that it's going to be north or south based on the sign of east or west. So let's just say that this represents the direction that an airplane is flying. This is what I would do. The x component is a negative value. So what do we get here? We get theta is equal to the inverse tangent of dy is 13.8, dx is minus 4.6. Leave the negative sign off, but this is what we do. 13.8 is positive, so that is north of. 4.6 is negative, so we'll say west. It's just that simple. If 13.8 were negative and 4.6 were negative, we would say south of west. And if 4.6 were positive and 13.8 was positive, we would say north of east. Now, what if you switched the direction? In other words, what if you did the inverse tangent of 4.6 over 13.8? Well, that's not really a problem. You're just giving the angle from the vertical axis. And you would, again, you still have to pay attention to the signs. There's no getting out of that. But if you wrote it as 4.6 over 13.8, then you would have to say that 4.6 is west of, and 13.8 is north. Okay, so west of north is this angle. We are, if we're out here at a town called North, we are west of it. That's this one. Now, if we do it the original way, then we're going to be north of East. So we're out here at a town called East, and we go north of it. Okay, so let's finish doing this calculation, and let's see what the angle is. So we're going to do the inverse tangent of 13.8 over 4.6. Make sure we close our parentheses and hit enter. And we get 71.6 degrees. So theta is equal to 71.6 degrees, but you must reference the x-axis. So we'll say from the x-axis. And if you don't want to say from the x-axis, if we're using cardinal directions, then just like I had up here, we would say 71.6 degrees north of west. This is theta.